Okay, I'm back. We'll keep going with this problem, this learning example. So we want the Thevenin's equivalent between these two nodes right here, here and here. We consider this to be an open circuit. Current equals 0. Infinite resistance, open circuit. So we can redraw the output impedance like this, right here, and write down the expressions. So it's 4 ohms times 2 plus j divided by the sum, 4 plus 2 plus j. Multiply top and bottom by the complex conjugate of the bottom, and you get this expression. And when I go to my calculator and crunch numbers, there's the calculator, I get 17.1 degrees and 1.47 ohms as the magnitude. Okay, let's see what they get. So they get 16.93 degrees. They got the same magnitude but different angle. This is supposed to be 9.46. If you take the angle of inverse tangent of 1/6, you'll get 9.46. In fact, let's do that right now. 1 divided by 6 equals, and then inverse tangent. There we go. 9.46. Okay. Then the matching impedance then would be identical, and this expressing this as a complex number. And let's see, did I get that? Didn't quite work out as a complex number. Let's go to new octave, because then it does work out as a complex number. So this is the complex number for the impedance, 1.41 plus 0.43j. Oops, wrong place. There we go. And then you switch it to a negative sign because you're taking the complex conjugate. Now let's figure out power, and we'll apply this equation. Now we already know RTH. RTH is right there. So we need to find VOC. And we get that by using current divider equation. We have total current going through here, so I1 is going to equal the 2 divided by 4 plus 2 plus j, all 3. So that's going to be I1. I1 times 4 ohms is going to give you VOC, and we have to multiply it by the current that's being divided. So let's take a look at that. So here we have the total current. This is the divider part, 2 over 2 divided by 2 plus 4 plus j. And then here's the 4 part, the 4 ohms, to get the voltage. So this is current here, this is I1 here, and then this is the 4 ohms to get VOC. And you plug and chug. Let's see, I did this in new octave. Let's take a look at new octave. And just plugged in the equation and got this value, and the angle for VOC is 9.46. There we go. Not 9.64. That was where it came in. I didn't get the absolute value of VOC, so let's get that. VOCM. VOCM. The nomenclature. A for angle, M for magnitude, equals absolute value of VOC. 5.26. There we go, 5.26. Now it's plugging and chugging. It's taking VOC squared, the magnitude squared, divided by 8 times RTH. So power equals VOCM raised to the second power times, or divided by, parentheses, 2 times 4 is 8, times RTH, well, that would be the real part of this imaginary number. So in new octave, the magnitude of the open circuit voltage squared divided by 2 times 4, 8 in other words, times the real part of the impedance squared, impedance, not squared, just the real part of the impedance. This formula right here. Let's see what we get. 2.46 watts. And let's see what they get. 2.45 watts. Why is the difference? Oh, okay, probably a rounding error, I'm guessing. Okay. Now the next problem has to do with, has a dependent source in it, you'll notice, right over here. So, just like before, the optimum load impedance is the complex conjugate of Thevenin's impedance. Here's the formula for power. With dependent sources, you got to use this equation. You can't use 1/2 Vm squared over R or 1/2 Im squared R. You can't do that. You got to do this. You got to go back to the beginning. And we can look at this circuit, redrawing it, VOC, instead of a ZL, we have a VOC here. Do KVL around this loop, anyway, we'll keep going with that. So the way I do it is I look at, we have a rise in voltage, so 4 angle 0 degrees here, going from here to here, and then we have another rise in voltage, plus Vx prime, then we have a drop, minus, and that would be 4ji1, and then I look at it as a drop here. Now Vx prime, this potential here, because the current is going this way, I1 is going this way, this potential here is going to be less than this one. But we have the sign convention here. That means Vx prime is going to be negative. Just remember that. But for right now, I'm just going to write it as a voltage drop, minus 2I1. And that's voltage, let's see, voltage drop, voltage gain. That has to sum to 0. And rearranging, then we get 4 angle 0 degrees equals the negative Vx prime plus 2 plus 4j times I1. Same equation they're getting, which is good. And when we take a couple different approaches, a couple different looks at things, making sure everything winds up the same is good. And then this reminds us what I said earlier, that Vx prime is going to be negative value. So we can make that substitution here. So that's 2i1 plus 2i1. So we're going to get 4 times a 1 plus j times i1 equals 4 times the square root of 2 I1 at an angle of 45 degrees. Okay, let's see what the book says. And so 4 angle 0 equals 4, yep, perfect, so far so good. I1. They brought the I1 factor over here, by the way, on the back side of the 45 degrees. And we just do the division, so that's I1 is going to equal 1 over root 2. You know, just 4 divided by 4 root 2. And angle of negative 45 degrees. Okay. And 1 over root 2 is this. So now we got to go on to find out the the open circuit voltage. Of course, that's going to be the this potential. Remember, this potential is higher than this one, and this potential is low. So this potential is higher, and this potential is higher. So we're going to have a plus and then a minus going on. Perfect, right there. Let's see, we already got I1, so this becomes 2I1, easier to say 2I1, is going to be 1 minus j. There we go. Square root of 2 times I1, 1 minus j. So there's the 1 minus j, 4 at 0 degrees, negative 3 minus j. Watch out for this, because we have a third quadrant data point. So the phase angle is going to be negative something less than 180. Voila, right there. And root 10, 3 squared plus 1 is 10. Take the square root of it. There it goes. And then, of course, 1/3. Just double check the angles work out. And we're ready to go on to the next part. Find the short circuit current.